Okay, folks, well, welcome to the beginning of class. It's 1 o'clock, so we're going to start. First, we're going to start with this. You know what that is?
That is a satellite from the International Space Station.
That is from the International Space Station. You're going to see this twice today. I'm sorry. But yeah, so this is a photo that was taken yesterday on board the ISS by an astronaut named John Hassan, I believe. Fucking amazing. So the things that you want to look at here that are really cool are, one, how high up the altitude occurs. So this is happening at altitudes of 120, 150 kilometers, where particles from the sun are ionizing here. Molecular oxygen, or sorry, lower down is, I don't know if you can see the red too. You want to turn the lights off in the back?
Yep.
Yeah, you can kind of see it underneath. See all this redness? Yeah, so all of that redness is also aurora. This green stuff is the stuff that you traditionally associate with northern lights. And then as you look towards the edge, you have a limb enhancement effect that Reed can tell you all about. Okay.
Yours.
What?
The floor is
No, like later. We don't have time for this. This is not what today's class is about, but this is what we call an aside. So cool things that I find that I have to show because that's my job as an educator. Okay.
If it was aside, then why is it up front? Out the back.
Fired. You're fired. You're fired. Everyone's fired. Okay, so what is this?
That is northern
USA! USA!
In fact, that is what that is. That is the USA. And this down here is a day 3 projection. So if you ever like looked on your phone and you go to this thing called the weather app and it tells you the future, and you're like, how does it do that? Nope. Fluid dynamics, very good. All right. Yeah, woo, back into class. Okay. So what we have here is a projection of this is a computational fluid dynamics simulation. I forget who does this one. There's 2 major groups. There's a European group and there's a US-based group, and they do prediction modeling for all sorts of important things, including hurricanes, which are not very good. You want to know when those are going to hit and who's going to be affected so you can evacuate appropriately. But what you're seeing here is basically a low pressure system up here and a high pressure system over here. This low pressure system, remember that fluid tends to go from hot to cold, from high to low pressures, but these whole things are moving. So if you have just 2 systems, you would expect, okay, there's a gradient, high to low. I'm just going to go down along that hill. But as you can see here, they're much more complex because the next day's evolution, this system is barreling into this system, and it doesn't tell you anything about the flow velocity. So if you look here, you have these little blue lines that are telling you where surge fronts are and the direction of motion. This is kind of tangential, kind of. It's not like a line, right? They're not contours. And so this is what's been barreling into the west coast of the US for the past, month and a half, is cold air from the north that's coming down, and then warm, humid air coming from this direction. Then they hit right here and they deposit a shit ton of snow. Okay. So this is the simulation going forward. And then going forward, one more is here. That high pressure system moves down, maybe gives us a relief, but might just ends up turning the storm more southerly. So you see up here, it's going to barrel into the Sierra Nevadas. And this is a picture from space. It's pretty fucking cool, in my opinion. My opinion matters. So these are clouds, not snow. But you can see satellite images before and after all of this snow. It's amazing. I'll include that maybe on Monday. There's LA, that's where we are. And what you see is basically this is a low pressure system that's swirling because, what's it swirling?
Say it again.
Why is it swirling?
Oh, it's that thing that we spoke about. That we said we wouldn't kind of go deep into.
Yeah. What is that called?
Turbulence.
No.
No.
Big swirls are not turbulence. Small swirls are turbulence.
Oh.
Big swirls are louder with more confidence.
Vortex.
Eddies are smaller. Whirlpools are in water. Vortices is the shape. Hurricanes are a result of the Coriolis force. So on a planet that is not rotating, the Coriolis force is much weaker and storms are much weaker. And we'll see that when we get to geostrophic flows and to geophysical fluid dynamics, okay? What? Yeah. Jupiter spins 9 hours and it's much bigger. So it's R crossed with V. And so you have a huge Coriolis force, which is why you have like 11 Hadley zones. Okay, we have 3 on each hemisphere, for example. They have 11 on each hemisphere. Okay, so this is what we're going to be learning today. So we have gotten all of the tools. We now understand all of fluid dynamics, and we're simply going to apply it for the rest of the class. Okay? You believe me? Fired. Okay, so remember, check-ins are this week. I've already met with a number of you, but not all of you. Some of you have not even contacted me. I don't know who I'm looking at, but I'm looking at some of you. Okay. Do this, otherwise I'll be upset. There's a homework. The homework is really fun. It's not a bad homework. Look at it now. It's posted. It's in the back of those lecture slides. And these first 2 are fun. You do a thing with fluids, like with your body, and then you do a little math, maybe. And the third one is really fun, but it will require coding. So if you need to brush up on your coding, let me know. Andrew, this is the book I was talking about. Okay. I'm sure there's an online copy of it somewhere. So do that. It will be straightforward coding. If you remember computational, if you didn't delete all that information, you'll breeze through it. If you deleted it, go in, restore trash, okay? And then make sure that you upload that back to your brain. Okay? If you have questions, ask sooner rather than later. We'll be using code a lot. Questions before we get started?
So from 4.28 to 4.7 required coding.
I just told you these will be with your body. You will do these.
Like a physical thing.
With your physical body. This requires using your mouth. This requires using your hands and water. Oh, what could they be? Amazing. Okay. All right, let's get started. What's this? Rolando.
Continuity equation. Oh, that specific term?
Yes, you got the equation, correct.
Okay.
Paolo, what's this term? No. We are not reading from the book. If you have the book open, you're missing the point of the exercise. This is not an opportunity for you to read off something that you don't understand. Okay? She looks down at her notes. Okay, this one here is what? Paolo.
I wrote it down with the next one.
Yeah, but what does it mean?
I don't remember.
Okay, that's fine. Desiree? Yeah, what does that mean though? Right, and so what's an analogy we would use with that? So the analogy, you just made a shape movement? How would you describe this? Okay, that's reading it.
Yeah.
What does it mean?
Unsteady.
It's the unsteady term, that's correct. And what does it mean?
I guess the amount of flow going into volume.
This doesn't say anything about the volume yet. But you're on the right track. Go ahead. Jasmine rose her hand. Yeah. Okay, that's not that. The second term is the advective term. Read. Yeah, so we are saying that the flow is changing with time. I am reading it, but what does it mean? What's an analogy you would use?
The getting fatter.
Eating,
Yeah, you're
right? If I put food in to my mouth, my density changes, right? So meaningfully, this is the change in density with time. Okay, well, what does that mean? Stuff was added, it became more dense, material was in there, right? How was that accomplished? Yeah.
Question, you always use the eating analogy. Like, for stuff,
Yeah.
but the density can also change. Here, is that not implied?
That's the reverse analogy. So if I go out drinking and then I throw up, right, that would be a loss in density. Right now, there's more air in the tongue.
Thinking how much stuff you have. You're thinking of.
That's this piece. Right? So this is the advective term. This is ddx rho ui. So if I'm changing my physical space, right, you're absolutely right. I could do PdV work. I could increase the volume, and that will change the density. And why are they added together here?
They really. One change in the other one.
One changes the other exactly and oppositely, right? So I could very easily put this thing on the other side and it would be negative. And that would tell me something really important. The rate of change of the density is only due to the negative gradient of the rho u, of the mass divergence flux, right? Not inversely related, negatively. Inverse would be flipped. Yeah. Yeah, what does advection mean? Giselle?
I know, is it you, that was thought of.
No, what is advection? Just the word.
I just think of.
Yeah, so stuff moving. That's the right way to think about it. Advection is the motion of something. So let's say I have a quantity F, unnamed quantity. That could be salinity, that could be temperature. I want to know how that's distributed. That's moving with the fluid. That would be the advection of that quantity. Right? So if it started over here and it ended up here, that's the advection of the quantity. Okay? Okay. So this term meant, Orlando?
Oh, that was the advection term?
Very good. Good. One down, 4 to go. All right, what's this one? Let's start in the back there, Isabel.
Total derivative of velocity times density.
Right? What does that mean? Yeah, what does this mean? Like in English words, just like when you get the vibe, like what do you think about it?
Not getting it.
Okay, John?
So it's like, it's how you're moving through the particle, or so the whole body, how it's moving through space, how it's changing, right? So you have something, so
Okay,
I remember the name of it.
okay. So it is the total derivative, right? And there is a portion of moving. That's the advective part. But there's also this unsteady part. How is it changing with time? Right? So what does this relationship left side equals right side conceptually mean? Not the terms. What is this equation called? That's right. Paula?
Higher derivative of something.
Yeah, what's the whole equation called?
Reynolds transfer thing.
Nope. Read. The Navier-Stokes equation. Okay. And what does it mean, Eduardo? No, not the terms. Just generally speaking, what does the Navier-Stokes equation talk about? Conservation of momentum. So to go back to your point, this first piece is the total derivative of the momentum, rho u. So up here, we said the total derivative of the mass is 0. This is a conservation of mass statement, and the conservation of mass says, I cannot create mass in any way. But this says something different. This says I can create momentum, right? And there's 1, 2, 3, 4 ways to do it. Okay? Jasmine, what's this first term? Yes, that's correct. And what does it mean? Okay. Giselle? And like intuitively, do you have like a description of how you feel this? Alex?
It's like the pressure forces.
Pressure forces. So if we think about a balloon that's light or low pressure, we pull it down and it's now at high pressure, it wants to go back up because it's being pushed up by pressure. That's the first term, pressure forces. Okay.
Does that mean that it's like when it's in space or in space?
Yes, absolutely. So this is always true, right? So for example, we looked in the very first week at something that moves up to a new pressure. And then once it's at that new pressure, we decide, does it keep going or does it stay there or does it fall back down again? Because it was a combination of two forces. And there's another force here. John, what's this pressure?
That is our body.
Body forces such as? Gravity. And explain that to people in the crowd.
When something has a mass, it experiences the downward force.
Towards the thing, right? Good.
Yeah.
Perfect. All right. So your analogy would be just like, some parcel of fluid is uniformly pulled, right? So this is a uniform pull. Okay. What about this one? Desiree? Yes, yeah. So these two terms are part of the stress tensor. That's right. So what is it? But what does the first part intuitively mean, Paolo? No? Rolando?
Isn't that the viscous word?
We haven't talked about work yet. This is all momentum. You can use hand emotions here too. That's not correct. Yeah.
The diagonal.
These are the diagonal terms. That's correct. And that means what?
Compression.
Compression, rarefaction, right? Okay. And then this last piece of garbage.
Rotation.
Don't shout it out. Come on now. He's too eager with the question. Read what's that last piece of garbage. Right. Does this make sense? Okay. Yeah. That's this. This is viscosity, that's viscosity, that's viscosity. Anytime you see a mu, it's either viscosity or it's sometimes the kinematic viscosity, sometimes it's the dynamic viscosity, sometimes it's the bulk viscosity. Who knows? Okay. What matters is that these are numbers. So in an inviscid fluid, this is 0. And all of these disappear. And then you get really easy stuff like the Bernoulli equations, right? Okay. So this piece up here, interesting. What is this whole thing mean? What was that?
Total energy of fluid.
Right. Very good. Okay. And what are the two pieces inside on the left-hand side, Eduardo? Okay, Giselle?
Was it like, so E is other energy, but the one half.
Yes. So the 1/2 is kinetic energy. I love that because I can always remember 1/2 U squared. What's E, John? Internal energy. What's another way to think about that? How do I feel about it? Thermal. It's really how the randomized velocities in our Amazon package are moving around. and different from the bulk velocity of the fluid. Okay. What's this first term, Paulo?
Another body force?
That's correct. But now it's not a body force, it's a body. This is a statement of conservation of energy. So this would be it's from the body forces, but it's a rotational. What's that?
Same letter for the back.
What? So what was this term? And what was this term? And what is this term?
Gravitational.
Gravitational potential energy. So it's from the body force, but we're talking about a new equation and we have new units. So that's an energy. Okay. All right, what's this P du dx, Rolando?
Is that the?
Nope.
No, okay.
Alex, what's the first one here?
That's the word. The PV.
Just this term, not yet what it means, because we haven't turned it into a V. So you're in the right place, but you said PV work and it's not quite PV work yet.
Pressure work.
It's pressure work. It's the work done by pressure. Okay, and we'll get to PV work in a second. This one here, Desiree? Yes, perfect. So when I see tau, I think stress. What kind of work is this? You said it kind of already? Yeah, stressful work. Another word for that is Lewis class. I heard that a lot. Y'all all fired, everyone get out. Jasmine, what's this term mean? Stress work or what was that motion? Yeah, so this is work in the stress. Let's move through the rest of the terms. We're going to see if we figure it out, okay? What's this one here? Fuck, now we really messed up because there's the same letters. So I can't just use letters in order to figure out what's going on. And in fact, if I look over here, I see UJ. Oh, fuck, that's in here? Oh, no. I've done a real bad. Okay, so what's this one at the very end? Follow. Giselle? Heat what? You're almost there. Heat something.
The gradient.
Right? Which is another word for that is the flow, heat flow. So Q is traditionally thought of as your heating rate or the heat distribution. So this is heat per unit volume, because remember it's little, it's an intrinsic variable, and this is the gradient of the heat volume. So how is this distributed in space? Okay, so now below we broke this piece into this and that. And we started with this. I took the momentum equation, I multiplied it by U, and then I took it away from this to get that, right? We did this all in class last time, and everyone super understood it perfectly the first time, right? So let's go through the term. I have this piece. Where does that piece end up? E. Where does this piece end up? Oh, good. Okay, perfect. Okay, where does this piece end up? Good. Okay, good. All right, where does this piece end up? Not on purpose. You hiding this? Good. Okay, where does this piece end up?
Where are you going here?
We got some questions. Is it here or is it here? Here or is it here?
I don't like it.
Hands for this side.
Oh,
Okay, hands for this side.
Oh, now that you pointed that out, I don't know.
As I said, there's some repeated looking terms up there. Fucking cray, right? Ah,
Okay.
what? The P is on the outside, so the P has got to be on the outside. Okay, what about this one? Where does it go? Okay, do you think it's this side or this side? Raise your hand for this side. Raise your hand for this side. No one got tricked into this side? That's because there's parentheses, huh? Oh, the parentheses help, okay? Because it tells you that they're conceptually linked. Okay, what's this one then? We're running out of choices so the game gets easier.
Sorry.
This one goes.
Left.
This one?
No.
This one? There you go. Okay, and then this one? So of course that one. That one's boring. Who cares? And then the last one is the worst. So let's think about what it means, because we had this issue where we were like, well, I understood what pressure work was, and now I don't know if I understand pressure work. And I understood what viscous work was, but that didn't make any sense when I saw it twice. How do you do it twice? I'm double counting, right? So let's look just at the first term. What does this mean? Read.
So that, that's like that's just like how. The food is like.
Okay. Paolo, what's that first term?
What again? Sorry.
One you took a photo of. You know the slides get posted online, right?
Yeah, but I need a.
Okay, that's fine. That's fine. Here you go. This one here. What does that mean? Alex, what does that mean?
Just like the term inside.
This whole thing in words. Because we've seen DDT a couple times now, and I haven't seen people like absorb it and then bleh, regurgitate in their own thoughts and digest it. Yummy. Aaron, what does this term mean? Like not just the words, but like what does it mean? That makes sense. We know that it's the total derivative, but what does it represent here? The change in kinetic energy, right? How? So there's two ways, of course, that this happens. One is the time. Well, the temperature is not here yet.
Is it time and space?
It's through time and space, right? So the change in the kinetic energy, you're absolutely right, as the fluid is moving around. So these are the ways that I can change the kinetic energy of the fluid, as opposed to
Changing the thermal energy.
changing the thermal energy of the fluid, right? And remember before, we had ddt of rho. We said that's 0. No ways to change rho. Only thing you can do is you can smush or increase, right? Smush, increase. These things change the density, but I can't add more particles to the system. Can't make mass. This one says there's lots of ways to do it. So what's the first way to change the kinetic energy of a fluid? Rolando?
The force.
It's not a force. Right?
The body work done on them.
Body work, another way to say this is. What's that?
Energy.
Another way to say that, and one word before energy is
Gravity.
gravitational what energy?
Potential.
Potential energy. Potential energy. The whole box moves. The whole box falls. I drop the box, it falls. That is the first way to increase the kinetic energy. By trading potential energy from the gravitation into kinetic. What's the second one? That's right. Anyone who looks down is the first person I look to. Yes, pressure. What type of pressure? Yeah, so think about this as an analogy, because we're gonna have two different types here. What kind of pressure work is this?
Wait, so you said what kind of pressure?
Yeah.
So like, give an example,
Yeah, give an example. I might have even shown one at the beginning of class.
or like, pressure of the tank or an atmosphere?
Pressure of an atmosphere with a high and a low region. The high and the low region, you have, for example, a gradient, dP dx, a gradient that's now going to force the fluid to smooth the gradient. Right? Right? Oh, super intuitive. I get it now. Perfect class, learned everything. Okay, what's this piece? Aaron? Viscous what?
Work.
Viscous work, good. And this is a little different than how we thought of this before. There's two types of viscous works that we're talking about here. What is this doing? Explain it how you would explain, like, to your friend, like, what does it really mean? You know, like, you're sitting down, you're having a cup of coffee, talking about work, viscous work. And there's two types of viscous work, right? So this one here is very different than this one because they affect very different things. Right. Okay, hold on. Let me rephrase this question. I'm not just thinking about what the equation says, but like, how do you have, what's the analogy that we're going to use to understand this type of motion?
Over the whole thing on turbulence last.
Yeah, is this the turbulent term? It's not the turbulent term. Isabel, what's this term?
I know it has to do with dispute, that's all I know.
Okay. Yeah, everyone got viscous, and I'm good about that. Catch up?
Yeah, let's think about an example of this wording.
Like,
Yeah.
you're
Kind of like
squeezing
friction?
So remember the words friction and viscous, they just refer, like we talked about, intermolecular forces, but they're not describing what's happening in the fluid. If I want to change the fluid kinetic energy, what do I do here? This is a pressure pushing from one side, which is high pressure, to a low side. This is a,
Let's slow it down.
nope,
I don't know if it's bad.
what's that?
I don't know what he's pointing out, but. Does it?
Does it add heat? No, not yet. This is a shear, remember? This is a shear, this causes rotation, right? You cannot rotate a fluid without viscosity. Does that make sense? Why would that make sense? Pressures are all face on. Okay? UG, that's a body force that works on the whole thing. This is getting a parcel to shear or rotate, right? That's what the stress term means. And it's looking for the gradients in the term that is going to drive the motion. So this is, go ahead. That's probably better when we look at the Bernoulli equations. Just like I can't create new, I can have a fluid that's in rotation with inviscid. You can create any fluid you want. But imagine that you have this cup, right? And there's fluid in here, okay? And I rotate the cup. How does that rotation that I've created now change the cup's initial condition, which is at rest? Well, nothing, because there's no intermolecular contact between the particles, right? So the cup would move and the fluid would sit there. It's translated, that force is translated through the cup to get it to move through the viscous force. Yeah. Yeah, so that's, well, depending on what we're talking about here. So that is going to talk a little bit about here, right? Where we're changing potentially the interior viscous work. So this piece here, we're going to talk about the different types of things that we can do. We can increase the heat. We can make the temperature go up. by dissipating viscous energy. Whereas here, this is like a shear force, right? And then I act across a distance, and that makes it an energy, viscous energy.
Can you just quickly go through like each separate little like part of it and say what they are? Like I have them all written down, but I think I missed like 2 of them.
That's what we're doing.
No, I know, but I didn't
Like
that was it, right? That was all of them?
I think he means like quick summary, like this is this,
I guess just a.
like a quick little word.
Like the name, like yeah, like a quick summary.
Okay, well, let's finish what we're doing, and then we can do it again, right?
Okay.
Okay. So this was the work that is done on the body, right, to increase its velocity. This piece here, we said was increasing the thermal energy, and this is, Alex, you had this earlier?
The pressure work for the
Yeah, pressure. What's that thing?
volume.
Pressure volume work. PV work. So here's my PV work. This is my. So we talked about this when we saw the swirls earlier. This is my vortices, eddies that become. This is correct. This is all correct.
Oh, it becomes heat.
Becomes heat. This is taking the bulk kinetic energy and it's siphoning it off, and it's turning it into heat. This is a heat train. What's this thing? Heat. What'd you say?
Flow.
Heat flow. This is the heat flow directly into the fluid. So these are forms of heat. So I change the energy, internal energy, by heating it. I change the kinetic energy by either trading with it gravitational potential energy, pressing on it to make it go fast, rotating it, spinning it, shearing it. Is that what you wanted to see?
Like that. We'll throw a whole topic. Just like that.
It's right there. All the lines are there. Okay, no, we can't spend too long on this. We have to do what we came here to do, which is to compute.
Don't worry, the book will have it.
And this is going to be a slide that you can take home, I promise
I
you.
know, but it won't say like.
We're going to do it every week. It's going to go faster every week, I hope. Otherwise, we're going to get fucked. Okay, so let's talk about computational fluid flow. My favorite part about computational fluid flow is the very first paragraph, very first line that says the equations are so complex that we can only find analytical solutions for a relatively few number of simple cases. So the whole book is about all the analytical solutions, and there's a tiny, tiny piece about computational fluid flow. So instead, what we're going to do, and you'll see at the end of this class, I'll kind of like flick through the rest of the slides, because we're going to do this weird thing where we jump back and forth between chapters 6, 5, and 4. We're going to grab a little bit, and then you'll need to know some more stuff, and then we're going to implement it. And then you need to know some more stuff, and then we implement it, so on and so forth. Okay. And I'll try and update those as we go. It'll just be the titles, and then I'll fill in the slides later. Okay. So we're going to let a computer do the work. It's my preference anyway. Math sucks. Math's stupid. And so what we're going to talk about here is for folks who took computation a long time ago. It's really simple. Okay. The concepts are straightforward. You are doing things like making arrays, and you're doing adding and subtracting. And you're just doing that over and over and over and over. Why does it become complex? Well, because computers only do what you tell them to do and not what you hope they will do. And more importantly, every single place that you want to do these equations, you have to make sure that it's correct. So here I have a fluid flow. I have an inlet with some fluid velocity here. And as it goes into the velocity, it encounters a larger area, and then the fluid velocity changes. Generally speaking, we can't just solve that. Seems pretty simple, but I couldn't give you the direct U at every location. I can only approximate it if I made some implicit approximation, so on and so forth. But a computer can model it. And the way that it does that is it looks at this entire domain, right? And it says, I am going to apply all of my equations of motion that you just saw at every location. Okay. So what does finite difference mean? Nick, we already talked about it. You came primed with the answers.
Isn't it the way we solve derivatives in the computation?
It is the way we solve derivatives in computation. So what does it mean?
Making up an approximate derivative.
We're making an approximate derivative. That's exactly correct. So what's a finite volume? Finite difference or finite volume? Yeah. So essentially what you're looking at here, and we'll talk about this in a few seconds when we talk about finite difference approximation. But imagine that you have a point here. Okay. In finite difference, if I want to know, for example, let's say I look at this piece here, and let's say there's diffusion in the fluid. So the flow is going like this, and it's going to diffuse, it's going to evolve. What is the natural next step for this curve to have? Well, if it's diffusive, it will go from this and it'll flatten out till it's flat, because that's what diffusion does, it redistributes it. So it says, well, I'm going to look right here and I'm going to look at my nearest neighbors and see what the slope is. And if the slope is high, I'm going to try and reduce it. So this is what we did in computing, right? We would grab nearest neighbors and we'd take differences to approximate derivatives, right? So I could look at every single point, finite difference. What's finite volume? Finite volume is to think instead of as points, think of this as a wall. And a certain amount of the fluid will pass through the wall. And we have some conservation equations that instead of being written as derivatives are also written as integrals through volume, right? Integrals through an area. You saw all those? You hated those in the control volume section, but in fact, they're quite useful here. So if you look, and I challenge you to do this for yourself if you want to, you can start with the 6.2. When we talk about the advection diffusion equation, he goes through a control volume section again. I'm not going to do that here because I think we have, frankly, too much work. Okay. Is there questions about the theoretical standpoint that we're going to start with here? We'll talk about differences in 1 second.
So when it says finite, it doesn't mean not infinite, it means not infinitesimal.
Yes, yeah. Instead of not, so when we talk about finite difference, okay? What does that mean, finite difference? What is this thing, by the way? Derivative, good. And what's the definition of the derivative? The limit. That's what? Okay, I'm going to use H.
I know it's over 8.
Yeah, it's
That's what I'm supposed to say.
after that, but yeah.
Nope.
Oh, it's not.
F of X minus F of X.
There's no X. I don't know what you're looking at.
Oh.
Well, I
so
have a
it has to
P
be
minus
F
There you go.
plus.
Very good. Sorry, I did every single part of that wrong. Okay. So that is the definition. That is a real derivative, right? Isaac Barrow, not Isaac Newton, proved this. When Isaac Newton came along and made it, he was like, I'm cool. And so then he gets all the credit. So this one here, as the limit goes to 0, that's totally possible on the computer, right?
Yeah.
No.
Oh, come on.
The limit goes, we just talked about this today. Okay, can the limit go to 0 here? Why not?
Because then it's over 0.
Because then it's over 0 and the computer gets really upset. I get upset too, you said. Okay, so in fact, what do we do instead?
Oh,
An
what if-
approximation, what's the approximation? What is the finite difference?
Yeah, if you make H instead of 0, then do it.
Okay, good. H is really small, it's not 0. And what do I write?
No, there's no limit, it would just be like f of t plus some small number minus f of t over some small number.
Mm,
Ta-da! That's the finite difference approximation. Very good. Okay, notice that it's an approximation. But it's not exactly equal. Okay. And this will become really important later. Okay. Great, we're making great progress. So let's start by thinking about the advection diffusion equation. So this is going to be a fairly straightforward conceptual problem, and we're going to model it. We're going to code it, and we're going to talk about how you do it today. So imagine that you have some fluid parameter. It doesn't matter what the fluid parameter is. It can be mass, it can be temperature, it can be salinity. I don't really care. What I do care about is that the only things that the fluid is allowed to do is that it's allowed to advect. What does advect mean? What's that? Move, correct, and diffuse. What does diffuse mean?
smooth out.
Smooth out, good. So if you look at this parameter here, the parameter is f. Good job using f up here, genius. What happens in the next step? In the next time step, this fluid parcel, the dark line here, has moved to the right. That's advection. And how does the diffusion look? Yeah, so the peak got lower, and what else happened?
Got wider.
It got wider, right? So in fact, we always talk about, say, if we have a Gaussian like this, and it starts to diffuse, what's the next time step look like?
Gonna mellow.
Exactly. Okay, and how does the diffusion equation look? That's a good question, thanks.
Like, wait, like the actual equation, like.
Yeah, what does the diffusion equation look like?
Um,
If I say something is diffusing, what would I use?
Sort of like a negative thing.
I'll need a negative term, that's good.
It's okay.
No, that's good, it's good.
It's good for- it's good for this. So you want the equation that like leads to like the diffusion part of it, so like only the diffusion?
I just want the diffusive part. When I say something is diffusive, what does it mean?
Once you're out.
Right, and what's the property that makes it want to be flat? What? Me? Low to high pressure, we're not talking about pressure here. You've ever seen that before?
Yeah, a little plus.
Of something like F?
Okay.
Would that smooth it? Yeah. Even one gradient would smooth it. Right? But two gradients would definitely smooth it. Because in fact, you saw this in computational. And of course, you memorized everything that you ever learned in that class. So that's why I can draw on it here. This would be the diffusion equation. No? Does anyone remember that? From computation.
I kind of do.
No.
Were you not computational, or is that one of the fluid things that wasn't what I was taking?
No, this is, we did computation, so we had the ground, we had the surface like this.
Yeah, the weather problem.
And then we had like, it got different illuminations throughout the year, and you had to figure out like how deep it went.
Oh, wow.
Yeah, that problem.
Oh, man, gotta get all that rust off, use WD-40 on those brains. Okay, so this is the diffusion equation, and it's got a del squared in it. So that's gonna fucking suck, because we only did one of them. We have to do two derivatives now? Oh, that seems impossible, right?
Yeah.
No, because we did it before. It's really straightforward. How do I write two derivatives?
But if you put a function,
What's that?
You make a function for the first derivative.
That's, you could do that, it's tricky. I don't want, I want to simple. What's that?
The one inside the other.
This,
What does the first derivative mean? You're both close, but you're not quite getting to what I'm thinking of. Tangent means the slope. Slope, right? So if we have the information here with maybe 2 points, point here and a point here, and a distance between them, that is the rise run, correct?
Yeah.
And that tells me the slope. What does the second derivative tell me?
Concavity.
The concavity or the curvature? How many points do I need? 3 minimally, right? So in fact, how could I write, let's just put the front door. Oh, we're going talking.
it should be like a particle power.
It's kind of.
It's funny how the computers get on it.
I didn't turn it on. That was a beast.
Fuck, that was crazy, okay. All right. Oh, hold on, I'm on the wrong side here.
It's safe with that.
So we have equation. We're gonna write it slightly different here. So we're gonna write the advection equation, diffusion equation for a fluid. And because it can move, we have a secondary term. So in this specific one here, I had an unsteady term, right? We're gonna tie it back to shit we already know. And here's the diffusion. So unsteady diffusion, no advection. Does that make sense yet? So what is the advec? No? Okay. This is the rate of change of a quantity F. How can it change? Okay, it can only change by diffusing away. Okay, but now I want to introduce a new term, and I'm going to introduce that term like a boss over here. Okay, so that's your unsteady term, the way that we know and love it, right? And some function F. And it's going to be a parameter, whatever, looks like that, I don't care. Plus some fluid flow, df dt. Oh, fuck. Oh, you know what? Let's make it simple. Let's make it one-dimensional. And how can that change? By what? Good. And how do I write that? In one dimension. Yeah, I'm only going to do one dimension here. Let's make it simple on ourselves.
It's
Partial.
Okay.
Or
Oh, there you go.
it's square.
It's squared, right? Okay, good. There's two of them.
Yeah.
Yeah.
So with respect to time.
Well, now raise your hand for X.
Hmm.
Raise your hand for T.
I think
it's one dimensional, the X, right?
Oh,
Raise your hand for X.
what is X? It's fine.
Yeah.
yeah.
I guess.
Okay. So on this side, it says, how does F change? dt F plus U of df dx. What does this term mean?
Our changes according to time and speed.
Yeah, so this piece here we saw was the,
Time.
which means The unsteady term, very good. This is the unsteady term the same way that this was the unsteady term over here, right? Same term.
Okay.
Okay, this piece here was
Oh, the advection.
the advection term. And this piece here is the,
That's does that just mean the continuity?
okay, I lost y'all somewhere in between here. Okay, remember that we're starting on the left-hand side and we're adding advection. So I'm recreating it over here and I've already added advection. Where is the advection term?
The capital U.
This one. So what does this have to be?
0?
This is the advection. This is the diffusion. And does diffusion have partial derivatives with time or with space? Spatial derivatives are diffusion derivatives. Okay. Anyone mad? Okay, you say yes. That's it. That's it. This is the simplest version I can give you. I could give you 0, but nothing happens. Very boring to simulate 0. Okay? And we're gonna simulate. We're gonna do this in class. Well, not physically in class, but we're gonna talk about it. So if you want to do this problem, we have to be able to describe each one of those derivatives in a meaningful way. And conceptually, what I want you to think about is a box. And I'm going to make a two-dimensional box, and I'll tell you why. What's that? Okay. So we can think of this in two different directions, right? I have two independent variables there. Is that correct? So which one do you want to be x and which one do you want to be t? Horizontal or vertical?
Yeah, that's like one models.
Yeah.
T horizontal?
If X, that is.
What about y? Let's do y.
Yeah.
There we go. Is that better?
Yeah.
Okay, so what does this look like? This is some string. And as time moves, I pull the string to the right, in this like imaginary timescape, like Marvel Universe. Okay. So every single point here, right? I'm going to what we call discretize, make it discrete. Okay? So I'm discretizing all these points. Okay. And in fact, I can go over one time step. And so on and so forth, right? Okay. Which direction takes me from one derivative in time to the, or one space in time to the next? Which direction? To the right. So I go from here to here with plus dt. Does that make sense? So I have every state, let's say I start up here at t equals 0. Oops. T equals 0 is right here. And then this is dt. And what's this one? 2 dt. What's this one? And so on and so forth, right? So I'm stepping from left to right in my simulation, and I'm representing all of the points here. Okay. If I want to find out what the solution is, then I have to use that on the right-hand side. And this is already setting up how we will solve this problem. Okay. Every single point here is going to have some waviness to it. And this piece up here will tell us where to go from there. So here I have an x and an x and a t. Right? How do I write the finite difference in t?
Okay, one more time.
How do I write finite difference derivatives in t? It's right there. Very good. It's right here. Right? So in fact, I could go down here. And I could do this. And I'd be like, oh, I get it. How would I do it in X? Is it different? X and dx. Right. Okay. So that will be something that I'm going to keep in mind. A single derivative is quite straightforward. A double derivative looks like this. How do I want to write this? Okay. Let me write this slightly differently because I realized I changed topics midstream here. That's a better way to do it. That way we don't fuck ourselves up. Okay. All right, triangle T. Okay, so what did I say? So for this one here, I said I can find the slope simply by taking some distance away. And I take the difference between them and I look at how big the interval was. Okay. This is a type of derivative called forward time. Moving forward in time, progressing forward in time. Okay. This piece here is a double derivative. This one's a little tricky, but you can demonstrate for yourself that this would work, right? So this will give me the curvature at that specific location. So this is the derivative at a point f of x. Now, in fact, I'm going to want to center both my derivatives. So I have two spatial derivatives I'll be taking here. One that's a single derivative in space, and the other that's a double derivative in space. This one represents my piece in the middle, whereas this one here is giving me what the next one is, right? So I want to center it. So I'm going to write something very slightly different here. I'm going to write it like this: d dx, or df of x is why did I do that? It still tells us our slope, right? It's still equivalent to what we were doing before, but now it's centered over the location that I'm interested in, right? It uses slightly more information, slightly worse approximation, because now the spatial step is bigger. It's okay. It'll be important for doing the computation. Okay. So in fact, if I want to know the derivative at a point here, okay, let's say I want to know the d dx here. What information do I have to know? Yeah, the function where?
Oh, the function at that value. Of x.
If I want to know the derivative here, okay, what is the, so we said the spacing in that direction is dt. What's the spacing this way? I did one. Sorry, guys.
Oh,
So you want a little one below and the one above.
Yes. Okay, so this here, that spacing is our delta x. That's gonna be built into the array. Gonna be normal spacing. Adjacent steps are delta x away. So if I want the derivative here, I need this information and this information. If I want the second derivative, what do I need? Say at this location?
Wouldn't you, wait for the second, oh, sorry, for the second derivative, wouldn't you need to know one in front of it, the one where it's at right now, and then the one behind it?
Makes sense? Conceptually? And we need to take steel wool for our brains, get all the rust off. I promise it'll feel good once you start working. Okay, so look, I have all this stuff that I want. I told you how to write the derivatives this way, and kind of that way. Right? Kind of. And then I have this garbage up here. Okay, I have some velocity u. Okay. I'm gonna assume that that's spatially and uniformly constant. Maybe it's not, maybe that's a fluid flow. Okay.
Use just a scalar. Be a scalar.
We are gonna treat it right now like a number. Yeah. It can become a value. Right, so for example, if you look at this derivative up here, okay, this is the function evaluated at x and t. This u is the velocity. This is the thing making the motion. So this could be a whole vector evaluated at x, y, z, and t. Okay. Right. Okay. What's d?
Oh.
It's a constant, and it's d for diffusion constant. Diffusion constant. Okay. So I didn't include it over here because I was careless. Okay. So in practice, we can make a discrete approximation, discretizing, making it discrete, making it individual, not infinitesimal. You can take this standardized equation here, and you can turn it into something beautiful. Okay. So I'm going to use ft. So let's say f evaluated at a time t plus h at a location x. Okay. Minus f. I'm not gonna have enough space. I don't know why I did this. Let's start all the way to the right. Okay. F at a time t plus h, comma x minus f at the original time t minus h. Oops. All over the time. Let's call it this one here. Okay, that's the derivative, right? Time derivative. Okay. Second term is just plus u evaluated at x and t. And then I have to do the derivative. And I wrote the derivative down there, so I'm just going to copy and paste it. Okay. It's f t easy, right? Super easy, just copy and pasting so far. The last part is the fucked up part. Okay, what's that?
Wasn't it the Boston?
Yeah.
The double derivative? Oh, the fusion constant?
Yeah.
The middle.
But the middle one there. So now I have x plus delta x evaluated at t minus f of x evaluated at t plus f x minus delta x evaluated at t all over ta-da! Okay. So this is the simplest thing you can do. And it still sucks. But it's actually fairly straightforward. So the first thing that you think about is all of these derivatives, they're solvable. They're just adding and subtracting and looking at the fluid velocity at a specific time. So for example, if I have an array like this, okay? All of the particles in here, let's say I create a for loop. And I start at this one here. Why would I start here? Because then you have something to reference. Yeah, but why wouldn't I start here at the top? It's a boundary. Boundaries suck, right? Because boundaries don't allow us to do a derivative past the boundary. So usually we have to state something called a boundary condition. Okay, and in fact, there will be a boundary condition in your problem that says either we set it equal to something or it changes however it wants. It can be unbounded. My favorite are periodic boundary conditions, where this is this point. So you just wrap it like it's a hat or a, you know, like a sort of like Burger King house. Right? Okay. So let's start here at this point. If I'm starting here at this point, then I just use my information about the derivatives. Okay, and I put them all in there. Those are just functions evaluated at a point. This first statement here, if I want to know what f of t plus delta t at a point x is, well, I can add, let's call this term A. Let's call this term B. Right? So this thing says delta t. Wait, let me write this down. What? Looks better. It's a lot easier when it's B and A. Yeah, much nicer. And that bottom part is, if you recall from computational, that's just Euler's equation. So this is as simple as saying I have something, and I want to progress it forward by a little time step. So what I can do at every point in that array is I can imagine that it's an entire array, and I'm just moving it forward one step at a time after I calculate A and B. And A and B are just pieces of an integral. So I can do this a number of different ways when I set up this problem. Okay, I'm going to have an array. I'm going to have my fluid quantity. Let's call my fluid quantity, what's the fluid quantity we want to model? Bananas. Okay, there's bananas in the fluid. Okay, and we're going to advect and diffuse bananas in the fluid. The banana concentration is going to start off high in some location. We're going to see how it moves. Okay, so I'm going to start with some bounded array. Let's say I have 10,000 points. I'm going to have a for loop that first works through all of the points to give me A and B. And then I just apply to this next location the previous location's values.
You're gonna do like the problem we had last time with like electromagnetic fields and like plotting them?
No. So it'll be much worse.
Oh, yeah.
Yeah. Yeah,
We did go through a field like that.
yeah.
Yeah.
For this one, we can do in one dimension, in one spatial dimension, we can walk through and we can use our past information. In 2 dimensions, it'll be horrible.
Yeah.
Because what's gonna end up happening is you're gonna have a fluid. Remember, we have a fluid like this. At every single location, we're gonna need to know, right, depending if we're doing finite volume or finite difference, you're gonna have to know what all the rest of those quantities are. So you'll have like 7 or 8 arrays that have the location of the fluid in, sorry, at every location of the fluid, you'll have the density, you'll have the velocity, you'll have each component of the velocity, right? You'll have u, y, right? Does that make sense? Was that your question? Or you want to?
Yeah, we're gonna do it next week with you, right? Or are we gonna do it alone?
No. You're not gonna do it alone. I wouldn't be as bold as saying we're gonna do it next week.
Okay.
So finally, oh, sorry, I already went over my time. God damn it. Okay. So this is forward time centered space. It's written in the book in a language that's the worst language I've ever seen. It's called MATLAB. It's garbage. Do not ever write in it or ever give me code in it, or I'll scream like a baby. So instead, we're going to be writing in Python in this class because it's beautiful, gorgeous language that has documentation online for free. And if you need this book, let me know. I brought it. What I'm looking for here, dust off your skills, pull out Anaconda, not the snake, the computing program. Put your code into Anaconda, play with it, right? If it breaks, send me a Slack message. Let's work on it together. We're gonna do, hold on. So I'm gonna show you all the places that we're going. First, I'm gonna skip to the end to show you the homework. Or first, end of homework. Okay, let me show you where we're going. We're gonna do finite volume approximation. Then we're gonna do implicit schemes. You'll remember implicit schemes from computation, like the Crank-Nicholson. You know what it is.
Yeah.
Okay, steady state problems and boundary value problems. This is where we're going to talk about what it means to have a boundary. We're going to look at 2D advection. This is the first time you'll see 2D. Okay, so still we're not boiling water. We're just putting bananas in the middle of the water and letting the bananas move around. Okay. You can also, some people like to use rubber duckies. Rubber duckies is a great analogy to use in your dimensionless equations. Sorry. Okay, Bernoulli's equation. This is when you know about barotropic and baroclinic. Then we'll talk about vorticity dynamics, and this will be inviscid flows. Okay, and then we'll do vorticity and inertial frame. And this is the first time we'll see real flows in streamlines. Okay, this is where we headed. No, that's chapters 4, 5, and 6, little pieces of. Not even all of 6, not even all of 5.
Oh, in B over there, why is it minus 2f of x to t?
It might be.
Okay.
Oh, yeah, this was a bad copy. Thanks for catching that.
So you're gonna go over homework?
No, I'm not going over the homework. The homework I showed at the beginning, but there is, let's see, where is it? Okay, code 1 here.
Yes.
It's written in MATLAB. You can stick it into Chat GPT. I don't mind. Just say translate this to Python. You'll basically change it into the advection diffusion equation here, but we'll use a different technique to solve it. Okay. I would highly recommend that you first try to just code this with this equation. Okay. This is not harder than you've done before. It's just different. Okay.
So code what you have on the board onto Python.
Yeah. Code that
Oh,
into Python and do that. Couple time loops, couple space loops, right? Oh, sorry, one space loop, one time loop. What's that? You should end up with the picture that looks like this. Save the whole array. You'll have something that's like X or Y, whatever, and then you'll have T, and it will have some like, right? Some will spread out, get wider as time goes on. That make sense?
Mhm.
Maybe,
Add it.
okay.